Everyone, do you know how missile guidance systems achieve precise control? In military applications, missile guidance systems need to precisely control the flight trajectory of missiles to hit targets. This usually involves real-time monitoring and adjustment of parameters such as the missile's position, speed, and direction, ensuring that the missile can fly along a predetermined trajectory. Missile guidance systems are closed-loop control systems. Hello, everyone. Welcome to the mini-lecture on intelligent equipment fault diagnosis and maintenance. Today, we will explore an important system widely used in modern industry, automation, and daily life, closed-loop control system. In this lesson, we will learn about 1. Working principle of closed-loop control. 2. Characteristics of closed-loop control systems. 3. Differences between closed-loop control systems, open-loop control systems, and semi-closed-loop control systems. First, let's discuss what a closed-loop control system is. Closed-loop control consists of an automatic control system formed by a closed loop made up of a forward signal path and a feedback path. So, what are the working principles of closed-loop control? Let's learn about them together. 1. Working principle of closed-loop control. A closed-loop control system feeds back part or all of the system output through certain methods and devices to the input end of the system. It then compares the feedback information with the original input information and applies the result of this comparison to control the system, preventing it from deviating from the predetermined goal. Closed-loop control systems utilize negative feedback, also known as feedback control systems. A typical closed-loop control system consists of a controller, a controlled object, and a feedback path. 1. Given component provides an input amount corresponding to the expected output. 2. Comparative component determines the deviation between the input amount and the feedback amount, often realized using an integrated operational amplifier, referred to simply as an op-amp. 3. Amplifying component. Since the deviation signal is generally small and insufficient to drive the load, an amplifying component is needed, including voltage amplification and power amplification. 4. Actuating component directly drives the controlled object, causing a change in the output amount. Commonly used actuators include motors, control valves, hydraulic motors, etc. 5. Measuring component detects the controlled quantity and converts it into the required electrical signal. Commonly used measuring devices in control systems include tachogenerators and photoelectric encoders for speed detection, rotary transformers, and self-synchronizing machines for position and angle detection, mutual inductors for current detection, and thermocouples for temperature detection, among others. These detecting devices generally convert the detected physical quantities into corresponding continuous or discrete voltage or current signals. 6. Corrective component, also known as a compensating component. This is an element with a structure and parameters that are easy to adjust. It is connected in series or feedback in the system to perform the required computational functions and improve system performance. Depending on its position within the system, it can be referred to as either a series corrective component or a feedback corrective component. Now let's learn about the characteristics of closed-loop control systems. Closed-loop systems are suitable for situations requiring high precision and stability, such as high-precision mechatronic equipment. Closed-loop control systems have the following characteristics in terms of control. Since the feedback amount of the output signal is compared with the input amount to produce a deviation signal, and this deviation signal is used to control or adjust the output amount, the system's output can automatically track the input, reducing tracking error, improving control precision, and suppressing the impact of disturbance signals. Besides, negative feedback-based closed-loop control systems have other advantages. Introducing a feedback loop makes the system less sensitive to changes in component parameters in the forward path, thereby reducing the precision requirements for components in the forward path. Feedback also makes the entire system less sensitive to certain nonlinear effects. Next, let's explore the differences between closed-loop control systems, open-loop control systems, and semi-closed-loop control systems. 1. In terms of feedback mechanisms, a closed-loop system can detect its output, compare it with the desired input, and then adjust its behavior based on this comparison. It includes a feedback loop that allows the output signal to influence the input signal, forming a closed loop. In contrast, an open-loop system lacks a feedback loop. Its output is only controlled by the system's input and is not directly influenced by the output signal. A semi-closed loop system falls somewhere in between, typically having sensing elements installed on intermediate transmission components to indirectly measure the position of actuating components. 2. Regarding control precision, closed-loop systems have a feedback mechanism that can correct errors in real time, thus offering higher control precision. Open-loop systems, lacking feedback, have relatively lower control precision. The precision of semi-closed loop systems lies between the two. 3. From the perspective of system stability, although closed-loop systems are precise, the introduction of a feedback loop may complicate and destabilize the system, especially when mechanical transmission chain errors exist. Open-loop systems, while generally more stable, lack error correction mechanisms, so their stability is also relative. Semi-closed loop systems strike a balance between stability and precision. Finally, let's further understand intelligent closed-loop control systems through a case study from everyday life. Suppose you are using a thermostatic water heater and you want the water temperature to remain at 40 degrees Celsius. When the water temperature is lower than 40 degrees Celsius, the heater automatically turns on to heat the water. When the water temperature exceeds 40 degrees Celsius, the heater automatically stops heating. In this process, the water heater functions as an intelligent closed-loop control system. A temperature sensor detects the water temperature. A controller compares the actual water temperature with the set temperature, and an actuator adjusts the heating power based on the control signal to maintain the water temperature near the set value. In today's lesson, we have learned about the basic concept, working principles, and characteristics of intelligent closed-loop control systems, and deepened our understanding through case analysis and practical operations. I hope you can apply this knowledge in practice and continue to explore and innovate. This concludes today's lesson. I hope that after class, you will review and consolidate your understanding and complete the following exercises. See you in the next lesson.